Hello viewers, welcome back to my channel. Today's topic of discussion is on allocation of frames. So this topic is under the heading design issues for the paging systems. So here you need to know the frames that are allocated to different processes. You know that the memory is divided into equal size partitions called as frames. So this I have been telling in so many sessions that if this is the main memory, then main memory will have what? Equal size partitions called as frames. Since you have number of frames, okay, in the main memory, how do you decide which process should get how many frames? So that is what is the topic here. Like there are different allocation algorithms. Based on those algorithms, the frames will be what given to the different processes. We have the equal allocation algorithm. In equal allocation algorithm, it is quite simple here. See how equal allocation algorithm works, I will tell you. In equal allocation, exactly what happens is whatever frames are available in the system, that frames will be divided among all the processes that are getting executed. That is, like I have written here in short notation also, split m frames among n processes. Suppose if the system has got 100 frames, fine, and if there are 5 processes, then what will be the this one? 100 divided by 5. Each process will get 20 frames. So here P1 will get 20, P2, let us take 5 processes, not P1, P2, P3, P4, P5. So each process has got how many? 20. Now here I have shown a very small memory, like that it will be a very huge memory. In this, let us assume there are 5 processes which are getting executed. For each of the process 20 frames are allocated. Now the processors have to make use of this 20 frames to complete their execution. This policy has got one disadvantage. This algorithm, equal allocation, has got one disadvantage. What I have written here in short notation, wastage of frames. Why are we telling wastage of frames? Wastage of frames is because what is happening, you know, suppose now P1 may not require 20 frames, P1 may require only 10 frames, okay, then P2 may require only 10 frames, let us take like this, then P3 may require only 15 frames, P4 may require 15 frames, P5 may require only 10 frames. Suppose if this is the case, each of the process is in need of, or P5, let us take P5 may require exactly 20 frames only. Just randomly I am taking. I wanted to tell you the main point that whatever is allocated to the process may not be in need of that many frames. Okay, out of 20 allocated, only 10 are in use. Then 10 will be what? Wasted. So here also 10 will be wasted, here 5 will be wasted, here 5 will be wasted, and here P5 is making use of all the 20 frames. Like that, wastage of frames may happen in equal allocation. So this is the problem with the equal allocation. So in order to overcome this disadvantage, there is another algorithm called as proportional allocation. So proportional allocation. So we'll take the system is having how many? 100 frames. Fine. Let us take that P1 is clearly demanding only 5 frames. Let us take, for example, P1 says that it needs 5 frames, P2 is 5 frames, P3 is in need of, P3 can carry out its job with 10 frames, P4 can carry out its job with 10 frames, P5 needs 20 frames. Okay. So this is the requirement for each of the processes. If at all we have to go for the proportional allocation clearly you can see here A of I here is what? The P1, that is 1, 2, 3 of process, that is frames allocated to a process I. AI indicates frames allocated to the process Pi, that is equal to Si divided by letter S into M. What each one of these indicates? Uppercase, this one in the denominator, whatever you have S, it indicates sum of the sizes of all the processes, and this in the numerator, it indicates size I of the process Pi, and M letter indicates number of frames in the system. So when you try to make use of this concept with this logic for proportional allocation, you can check here. See, first let us take, you want to allocate it to P. AI is what? Now I am taking P1. P1 is SI, SI is what? Size I of the process. That means this P1 needs whatever is the size of the process, for that size it needs 5 frames. So let us take 5 divided by sum of the sizes of all the processes 20, 30, 40, 50 all put together is how much? Sum of the sizes is 50. So this one into m is what? The system is having 100 frames. So if this is the case, how many frames P1 will get? P1 will get 10 frames. Okay. P1 is getting how many? 10. What about P2? Yes, P2 is also having the same value. It is asking for 5. 5 into 50 divided by 110. So P2 will also get what? 10. P3? P3 is having what? P3's request is, P3 wants 10 frames. Okay, 10 divided by 50 into 100. So P3 will get 20. P4, you can check here. It also needs 10 frames. 10 divided by 50 into 100. Okay, it also gets how much? 20. What about P5? P5 size is 20. So for that P5 size of the process, 20 frames are needed. 40 frames it will get. How many? 40. P5 will get 40. Fine. So 40, 50, 60, 70, 80, 90, 100. In this way, we say this is what is the proportional allocation of frames done in the system. This seems to be quite reasonable and has got a logic also, because the processes are not going to waste the frames that are allocated. Depending on the size of the process, the frames are allocated. That's the reason here we can say this proportional allocation is quite reasonable. But one important remark you can remember here, if multiprogramming increases or decreases means what? Now at present you are having 5 processes. That is how the distribution has happened. Suppose if the number of processes increases, then what will happen? Proportionally the number of frames will be less here for each of the process. Suppose if the number of processes decreases, that means it is lesser than 5, then the number of frames each of the process will be more now. So depending on the number of process, that's why we say multiprogramming is going to decide what the number of frames that are getting allocated. We have now the global replacement allocation. In global replacement allocation, first the word you see, replacement. So this replacement algorithms you have learned, page replacement algorithms. But what does here global replacement? It is completely related to what? Frame allocation only. So global replacement allocation. Normally what is that? CPU wants to execute an instruction is present in the page. Okay, if that page is present in the memory, no problem, CPU will execute. Okay, if the page is present in the memory, there is no issue at all, the CPU will execute that instruction from that page. If the page is not available in the memory, then what to do? Then the page has to be brought from the backing store, that is the hard disk, and it will be placed into the main memory. As long as if there is an empty frame, no problem, the page will be moved here into this empty frame. Suppose if there is no empty frame, all frames are filled with pages, then one of the page has to be replaced here in order to bring in the new page. That is what we said, no, it is replacing a page. And whenever a CPU does not find a page in the memory, we say there is a page fault happening. Now global replacement allocation is, for each of the processes some frames are allocated. Like let us assume that in this memory there are 2 processes. Okay, for each of these processes some frames are allocated. Let us take 20 and for P2 40. So now suppose if process P1 is in need of extra frame, then it can always take a frame from process P2. Fine. If process P2 is in need of an extra frame, it can take a frame from process P1. Whatever is allocated to P1, it can borrow from P1, and whatever is allocated to P2, P1 can borrow from P2. Like that, whatever are the number of processes, they can borrow from each other. That's why we say here globally. All the frames are present there, okay, belonging to all the different processes, all the frames are available. Each set of frame is belonging to one single process. Whenever a page fault occurs, somehow the process, even if there is a shortage of frame for that particular process, it can borrow a frame from other process. So if the frame is available, then the page can be brought easily to the memory. That's why the execution never stops here. And we say since the execution is not getting stopped for any of the process, and system throughput will be greater here. But what is the disadvantage here? Page fault ratio and pages in memory that are there, they are affected by the paging behavior of the other process. It is not only, see, any page fault or whatever pages a particular process has got in the main memory is not affected just by the paging behavior of its own, but also it is affected by the paging behavior of the other processes, because only if other processes have got their frames free or available, then this process can borrow from them. So that is why we say it is affected even with the paging behavior of the other process. That is the disadvantage. But whereas for local replacement is for whatever frames, suppose local replacement allocation works in this manner. If there are processes P1 is assigned with 10 frames, P2 is having 20 frames. Local in a sense, now P1 should manage only with whatever frames it is allotted with. P2 should manage with only frames that whatever it is allotted with. So there is no question of P1 taking from P2 or P2 borrowing from P1. That's the reason we say it is a local allocation. If at all there is a page fault happening here for P1 should see that if frames available, then only it can bring in the new page. Fine. So here, that's why we say in local replacement, whatever disadvantage we set for the global becomes the advantage here. It's not at all depending on the paging behavior of other processes. Rather, the pages that are there, okay, available in the memory for this process depends only on the paging behavior of this process only. In global replacement also, I wanted to tell you one more point. If globally the frames are available, normally a higher priority processes may take frames from the lower priority processes. Always importance is given to what? Higher priority processes. So most of the time what will happen in global replacement is the higher priority processes will borrow frames from the lower priority processes. If they get more frames, then in global replacement, the number of page faults for higher priority processes gets decreases because they are having more frames now. Whereas lower priority processes, the page fault get increases. That is one important thing to be observed here in global replacement. Hope this session is useful to you all. If you find it useful, please like, share and subscribe to my channel. Thank you. Bye bye. Take care.